stealth technology, the internet, GPS in the palm of your hand, autonomous operation.
Technology is a driver of our times. Since its founding in 1958 in the midst of the Cold War, DARPA, the Defense Advanced Research Projects Agency, has been a driver of technology. Welcome to Voices from DARPA, a window onto DARPA's core of program managers. Their job, to redefine what is possible. My name is Ivan Amato, and I'm your DARPA host. And today I'm pleased to have with me in the studio Fariba Fahroo, a program manager since 2014 in DARPA's Defense Sciences Office. Throughout her career, Fariba has been working on mathematical innovations and applying them in areas ranging from spacecraft control, vibration control and structures, and even to the vexing problem of quantifying uncertainty in the mathematical models that scientists use to study complex phenomena like weather and biological processes, and that engineers use to design, simulate, manufacture, and operate many of the complex technologies important in military and civilian settings. Thanks, Fariba, for spending some time with me today.
Thank you, Ivan. Good to be here.
I'd love to start out, Fariba, learning a little bit about you, about your background, your education, some of the important things that have happened throughout your career that ultimately led you here to DARPA. So tell us a little bit about that.
Well, let me tell you a little bit about my background and tell you that actually my relationship with mathematics has been a developing one. And I have to say that over the years, it has really deepened. I was born and raised in Iran, which has a long tradition of excellent and rigorous mathematical and technical education. I received my bachelor degree both in applied math and physics from UC Berkeley. From then, I went to the beautiful campus of University of Wisconsin-Madison. And then I went to Brown to get my PhD in applied mathematics. After getting my PhD, I came back to Naval Postgraduate School to California, to Naval Postgraduate School in Monterey, and spent several years as a professor in the Department of Applied Math. And while I was there, I was contacted by a colleague of mine who was working in very similar research areas. She suggested whether I would consider getting a job as a program manager for computational mathematics at Air Force Office of Scientific Research.
So AFOSR.
AFOSR.
And where is that located?
It's Arlington, which is basically on the
right,
same block as DARPA.
Right near us.
I wasn't even sure what that entailed. But having my colleague and friend in that position and watching her, what she was able to achieve was actually an inspiration. And that's when I said yes.
And how then did you make the direct connection here with DARPA as opposed to being a PM elsewhere?
The interesting thing was that about maybe a couple of years into my job, some program managers from DARPA approached me, and they said that whether I'd be interested in coming to DARPA. And I have to say, if I thought getting a position at AFOSR was scary and kind of out of character, I thought coming to DARPA would be the scariest thing to do. I had become familiar with research that had been supported by DARPA and DARPA's mission. And I was having a hard time trying to see how supporting basic research in mathematics could be of any relevance to what DARPA was doing and making that connection.
You certainly have done that with your programs, which we will talk about in a little while. You really have discovered that there really is a connection between you and the programs at DARPA. Before we actually talk about those, I want to pull back a little bit and find out how you and mathematics became lifelong partners. And I ask you this because this is true for me, and I'm sure many listeners, that mathematics is just one of those fields that for so many of us is difficult. We kind of push it away at the earliest time that we can. And yet you really had this partnership throughout. So how did you develop this, what I imagine is a kind of love for this discipline?
So my interest in mathematics was not actually from the point of view of being interested in abstraction or just because this was the way my mind worked. I was always interested in problem solving, but I was also interested in gaining better understanding, actually, of the physical world. So I didn't want to become an engineer, even though at the time it seemed like all those smart kids who with strong mathematical abilities would either go to engineering or they would go to maybe medical school. But then I decided, no, I wanted to actually become more of a scientist, so I was thinking of physics. The only thing is that I started as a physics undergrad, but it only took me taking a semester-long course in their experimental side to realize I don't have a lot of talent. I realized it didn't necessarily come with a lot of pleasure and joy spending my time doing experiments. So then I decided that actually what really gives me a lot of pleasure in studying hard was actually the more mathematical aspect of the physics courses. And I found out that, I can actually very quickly become a double major in applied mathematics along with physics. So that's how it started.
So what interests me about applied math is that in that way of engaging mathematics, you are looking at these symbols and working with these symbols that many of us associate with math, and you are finding out how they relate to the real world in pretty dramatic ways. One way of making this concrete in this conversation might be for you to tell us about how you applied a kind of mathematics and kind of an innovation for which you now have some mathematical entities named after you, and how that led to operational changes with respect to the International Space Station. So can you just tell us that story about that math to space station connection?
So the research that I was doing during my PhD and afterwards had to do with control and optimization of natural systems that are modeled by partial differential equations.
So what's an example of a natural system or two that fits that?
Sound waves, for example, control of electromagnetic waves, structures, or any combination of interaction of these different physical phenomena. So in the case of, for example, spacecraft control, is that we are looking at the situation where you're looking at complex nonlinear dynamics, where in this case...
So that means little changes can lead to big results.
Possibly, even though it's an engineered system, right? This is not necessarily like climate that you would say, well, we necessarily don't have any control over the innate randomness of the situation. But here we're talking about an engineering system that we would like to perform certain maneuvers in an optimal fashion. So you're expecting your system, in this case, spacecraft, needs to perform certain maneuvers that would, let's say, minimize certain objectives. So in this case, you're trying to do it sometimes in minimum time. Sometimes you're trying to do it with minimum energy or minimum
or
fuel,
propellant,
depending on
just so listeners can understand why that's something to go for, is propellant on a spacecraft can cost $10,000 a pound. So if you can minimize that. And
give that video. Not only is the cost, but also cost of, like in the case of International Space Station, the cost of refueling could be millions. I mean, that's the situation. So you really have to use everything in the most cost-efficient and optimal manner. So in this case, for me, actually, I have to say that the whole success story here, I owe it to my, basically my colleagues who were able to basically get the theory and the algorithms that we developed and basically work really hard to implement it on the space station.
Right, and if we were to say simply what the result was, if my reading is correct, is that you were able to come up with a way of using certain systems like gyroscopes on the space station to achieve fairly dramatic changes, like 90-degree turns, 180-degree rotations, without the use of propellant, or at least minimizing to a great degree the need for propellant, right?
Exactly. And this would not have happened had we not come up with an efficient and accurate way of implementing these
Right, but
maneuvers.
The actual controls that went to those gyroscopes emerge from the mathematical frameworks
Exactly.
that you were able to develop. And so this sort of draws that line all the way from this most abstract way of thinking,
That's true.
math, all the way to this multi-million-dollar savings of how you operate the International Space Station. That, to me, is sort of one of the miracles of math and its connection to the real world. So actually, let's segue then to you and DARPA and the two programs that you are working on here. So one of them goes by the acronym EQUIPS. That stands for Enabling Quantification of Uncertainty in Physical Systems. The other one goes by the acronym MODEL. That stands for Models, Dynamics, and Learning. So let's start with EQUIPS. And again, that stands for Enabling Quantification of Uncertainty in Physical Systems. This sounds fascinating, the idea of quantifying uncertainty. Tell us about the program, what the goals are, and what the status is at the moment.
The goals of the program, I have to say, in a sort of lofty fashion, which is not always my normal state of way of stating.
Well, we were just talking about the International Space Station, and that's pretty lofty. So
yes, but I do have to say that I had very lofty goals for the program, and the way in my mind I was thinking of the program, and I still do, is to drastically change the way we go through our modeling and simulation of what you were saying, physical world, engineering system. We do have a long history, basically almost all of scientific history of modeling physical systems and physical phenomena and using mathematics. But what I'm saying about changing the practice of modeling is in some ways taking into account how good or how bad we are as modelers. It's almost like bringing a certain level of honesty to our modeling, in a sense that we have to consider the fact that it doesn't matter how good we think our models are. At the end, they are just going to be an approximation. It's just going to be a surrogate for the physical reality. The fact that in the process sometimes we are not quite clear about the, let's say, the discrepancy between what the output of our models are and what the physical world is, it's going to create a lot of issues when we're trying to analyze a system. As far as physical modeling goes, probably one of the most successful stories is basically the Navier-Stokes equation.
So you might apply the Navier-Stokes equation, for example, if you wanted to try to describe how the cream you pour into your coffee goes into that fluid and you see the beautiful swirls. Or it might be the way masses of air in the atmosphere are flowing.
Exactly.
And intermingling and so forth. That's the range that we're talking about with this
Yes,
powerful
exactly.
equation.
Yeah. So air, basically flow of air over, airplane wings, or it's basically the fundamental of aerospace engineering, the celebrated equation. But the problem with it is that you talk to the people who are looking at basically physical flows, fluid flows, and they do still scratch their head and it still can say that we are talking in a certain situation, let's say in hypersonics, where it's not at all clear that this equation even held. If you were still talking about fluids, but it's at the scale and sort of physical condition that it's not at all clear that this is the right equation to even try to simulate. Yes, we do have airplanes that fly. We do have, aerospace industry has been one of our most successful modern industries, not the 20th century, and it will be even more in 20th and the future century. But it makes you a little worried that some of the work and the mathematical work that is being done is based on certain assumptions that and physical models that may actually not hold.
Correct me if I'm wrong, but as you were speaking, I'm realizing, well, we have these technology wish lists, right? We want hypersonic vehicles and hypersonic technologies, things that are sort of operating faster than the speed of sound. But what you're saying is we've got mathematical equations and traditions in math that apply roughly in the kind of phenomena that are applicable in designing a hypersonic vehicle, but we actually don't know.
We don't know
if it's an accurate representation of that, sort of hypersonic arena.
This need for quantifying our uncertainty or lack of knowledge, and also the kind of error and discrepancy that we have between our mathematical models and the physical reality and our engineered system, comes from engineers themselves. Because one of the things is that they are looking right now in situations that the only way they can, let's say, certify, let's say, their design or whatever they build is by using something, right? And in this case, they probably try to do it using tests. Well, in certain situations, you can test. And maybe you can, if you do test some any kind of testing, maybe you can do it in certain components of it. But full testing on the system, for example, let's say on the whole plane, will necessarily have to be done on the entire one. It's after you've already built it. That's a little too late in order to come up with ways of changing the design or changing the way it's being built, right? So you would like to be involved in that whole process as a mathematician and as an engineer a little earlier into that. So the only way to do that, testing is not going to help. First of all, in certain situations, it's maybe too expensive, it's too late, and sometimes impossible, is using simulation. The whole thing about simulation is based on having a mathematical model and having the simulation tools, like basically these numerical methods and all that, and the computational tools and platforms, so the computers, that you can actually do these simulation. So this is when you see that math comes in right there. And this is the only way that we can test out these new designs or that are not built, but you have basically the elements of the design, so you can at least test it out using simulation before you build it.
So I think I heard you once talk about this as almost like a mathematics of honesty.
Yes, it is.
And I love the phrase, now that you're talking about this world of simulation, which is based on mathematics and then perhaps mathematical models operating in the form of computer models. But in that kind of abstracted place and abstracted operation, you're trying to develop a framework with equips that is kind of the reality check in the math.
Yeah, exactly.
And how well is this representing ultimately the real world technology that we want to emerge out of this mathematics and modeling? Is that
yes, that's a very nice characterization. And what is so fascinating about this is that the field goes very quickly from some in the beginning may think some philosophical rumination about what is reality, what is representation of reality, what is the relationship of mathematics to the physical world, very quickly to some beautiful theory. The interesting result that I expect from equips is to see whether it's possible to come up with some common frameworks and common tools that could deal with some of the major challenges within looking at very different application problems. This is going to be an interesting process to observe and see what results come out of it, because the performers at this point are looking at system as different as possible from each other, from aerospace structures to integrated circuits to chemical networks. So we'll see whether something common will come out of the effort.
Well, so maybe that's a nice cue to talk a little bit about the model's dynamics and learning program.
So there's actually a very nice link between the program equips and model. One issue that I need to emphasize about equips, because right now I've only talked about it about basically, as you mentioned, it's about trying to capture or make honesty as part of our modeling process. But I haven't really told you about the challenges that we have in our process. And one of the biggest challenges is that the complex world that we're looking at, the complex system we are looking at, they're high dimensional.
When you say high dimensionality, what do you mean by it? It sounds like there's many parts that we have to think about.
Right. Exactly. So a lot of times when we think of dimension, and you have heard it, that you're thinking about there are 3 physical dimensions, and then we have dimension of time. So we think of physical world as basically like a 4-dimensional space-time. But the way we are using dimension basically here is what we think exactly. It's the degree of freedom, or basically the number of variables that we need in order to build our model or represent a model.
So if I have
variable.
a robot with 10 joints,
Right.
is that, I could think of it very simply as a 10-dimensional problem.
That is, exactly. So, but
But it could be 1,000. It could be very complex.
Yeah, exactly. And the interesting part is that you look at a robot and you look at it, okay, when I want to write down basically what I'm thinking about, the number of variables or modes or whatever that I can express, the physical variable that I'm interested in. But at the same time, sometimes when I want to do any kind of approximation, right, of each of these 10 variables or 10 dimension, for each dimension, I may actually need additional dimensions in order to approximate. So this is like at every step of our modeling here and approximation, we are introducing more dimensions here.
Right.
So starting at 10 what we say is a 10-dimensional system ends up being, for example, for each dimension, I may need another 10. Yes, as you can
Well,
imagine.
just a simple way of seeing how 10 dimensions multiplies in that robot case is that each joint itself has these 3 spatial dimensions and the temporal, so each one has 4. So suddenly we're already at 40 dimensions.
So sometimes those dimensions have to do with the physical, relates to the physical representation, but sometimes dimension comes from our approximation and the modeling and the mathematical work that we need to do. So it's an extremely good question as to what when we talk about high dimensionality, what we are saying. And this is what happens with the systems that we are looking at, that representation of these physical systems require lots of dimensions, lots of variables, lots of high dimension.
And the higher the dimensionality, the harder it is to compute, to put it into a computer and actually run a simulation.
It goes back to how much computing can we do. And people say, well, right now we do have extremely good, extremely fast computing platforms. And that is true. And that's why at this point we can do computing physical system that 20 years ago was not possible. But the more you do, the higher the demand on your analysis tools. Now about model. So model is a sort of an acronym for models, dynamics, and learning. And I would say that the goal of the program is extracting mathematical models from dynamic data sets. The goal of a program, I would say...
So let's just stop there. When you say dynamic data set, so I'm thinking a lot of data. Dynamics makes me think of motion or time. Did I get that right, or would you want to...
No, absolutely. What I mean by dynamic data set is a data set that you get from dynamical system, which are systems whose behavior changes with respect to time.
So you, Fariba, are a dynamic system, and
absolutely.
I am too, right?
I mean, it's just life is dynamic. It's a greatest example of a dynamical system. One of the reasons that I wanted to have this program was also, again, seeing that existing tools that we have or modeling cannot handle some of the complex dynamical systems that we need to analyze. We're looking, again, very similar, but we're looking, for example, at systems such as weather, fluid, biological systems, even engineered systems like communication networks or, human social networks. These are all examples of dynamical systems, but we don't have very good analytical and mathematical models to express the complex behavior of these systems. If you just look at a data set from something like turbulent flow, it's fascinating because you see these vortices, these holes, these eddies, these beautiful patterns come and go.
Right, and this is applicable in rivers, but it's also applicable in a jet engine.
Exactly. That's what's so beautiful about all these different complex phenomena that can be expressed. And when you see it, there's some commonality in there. And in this case, what we're trying to learn is that what are the common patterns that can be learned? And basically express dynamics of these systems in terms of evolution of these patterns.
Yeah, I see what you're saying.
We don't have the mathematical tools yet to deal with the data. So people say, why, look at us. Not only we're at the age of big data, we're also at the age of machine learning and all these different ways that we can handle data of any size. But what I'm saying is that the existing techniques cannot handle the fact that data is dynamic and changes with respect to time. And I'm actually now going back and say, look, go back to the beginning of dynamical system theory and trying to develop a different way of modeling, extracting these models from dynamic data sets.
Okay. Give me one example of a phenomenon, a system, a technology that cannot really be modeled well now, that if your model program is successful, will be modelable.
I've asked the performance and model program to start with something that we think we have some grasp of and use it basically as a test case and going back again to the classical problem of basically turbulent flow. My hope is that they can apply the methodologies, the mathematical methods that they develop to systems that are much less understood. And there are systems, for example, the data that you get, for example, from neuroscience.
So you're talking about things like how brain signals propagate or how patterns of neural activity associate with sensory stimuli or the way we move.
Absolutely. It could be data that you can get even from social networks and social systems, and basically to systems for which we really we're lacking the proper mathematical modeling strategies.
Before our time runs out here, I just want to ask one question about being an applied mathematician at a place like DARPA. One of the phrases you hear a lot here is the innovation ecosystem, and what that means is it really is referring to kind of all the players and all the stakeholders that it takes in order to go from sort of an idea about a technology to a technology that you have in hand, that's operational, it's in the field. So as an applied mathematician, what do you think you can do here that you might not be able to do elsewhere?
I say DARPA is probably the best place to be if you are an applied mathematician. In fact, I just say if you're a mathematician and would like to solve problems, because one of the greatest thing about DARPA is that there is this wealth of information, wealth of problems that are important, and I have to say they're very, very cool. The coolness factor for problems to solve for a mathematician here is enormous, because you feel that not only you're solving a problem that has importance, there's certainly broader impact as far as you're solving important problems in national security, but you also feel like the problems are so rich that in some ways there is so much to contribute. The richness of the problems are just is maybe the biggest driver, a motivating factor for anybody, certainly for a mathematician. And I just want to add that is that, and I've been saying that to my friends, to my colleagues, anybody who would listen, that why mathematics is actually very important to DARPA, and encourage them to come. As future program managers, is that when you're encountered by important problems and you see that your ideas, the role you have as a mathematician, that not only you try to look at these particular problems, but you try to abstract out and coming with different representation that would yield a better solution for these problems. So you basically see that your ideas are at work. I mean, what better satisfaction are there?
Well, Fariba, it's been a delight for me to talk to you about your love of mathematics that's coming out here right now, and to get some sense of how mathematics does have that role in the overall innovation ecosystem, and in particular here at DARPA. So I just want to thank you for spending this time with us.
Thank you, Ivan. It's been a pleasure.
And thanks, listeners, for sharing this time with Fariba and I. And I hope you join us again for the next Voices from DARPA. For more information about Fariba, her programs, and the other breakthrough technologies DARPA is working on, visit darpa.mil. And for links to allow you to download the podcast, go to the Voices from DARPA page on DARPA's website.